I am going to start with another topic, that is multi-objective optimization. Now, till now we have discussed a number of optimization problems and how to solve it, and each of these optimization problem is having only one objective. Now, these problems are known as single objective optimization problem. Now, I am just going to concentrate on a few others optimization problems in which we have got two or more than two objectives. Now, these problems are known as the multi-objective optimization problems. So, multi-objective optimization problems are problems involving two or more than two objectives. Now, let me take one example. Supposing that Mr. X is going to purchase a car. Now, before he takes the decision which model to be purchased, he generally tries to find out some information of the different models available, and while collecting information, so he will try to find out the information regarding the cost of a car and its accident rate. Now, supposing that, so here I am just going to consider two objectives. Now, Mr. X will try to select a car at the cost of a minimum amount, and at the same time the accident rate should be minimum. So, if I consider these two objective optimization problem, now let me just concentrate. Supposing that I am just going to plot the first objective, that is say the accident rate, and the second objective is a cost of a car. So, aim is to minimize both the cost as well as the accident rate. Now, the cost, supposing that this is denoted by C and accident rate is denoted by A. Now, aim is to minimize both cost as well as the accident rate. So, what he will do is, he will try to formulate another optimization problem, single objective optimization problem, and that is nothing but minimize the cost multiplied by a particular factor W 1 plus the accident rate A multiplied by another factor W 2, where W 1 W 2 will lie in the range of 0 to 1 and sum of the W values will be equal to 1.0. Now, if I just say one set of values for this W 1 and W 2, let me consider say W 1 is say 0.4 and W 2 equals to 0.6, and if I solve this single objective minimization problem, so there is a possibility that he will be getting a particular solution, say this particular solution say. Now, if he changes the values of this particular the objective function, the values of the weights like W 1 W 2 to some other numerical values, there is every possibility by solving this single objective minimization problem, he will be getting another solution. Similarly, by selecting the different sets of values of W 1 and W 2, so he will be getting different such solution. So, these are all optimal solutions in some sense. Now, after that what he does, he will try to put or he will try to fit a curve. Now, that particular curve is nothing but the locus of all optimal solutions. Now, this is nothing but is actually the Pareto front of solution. This is known as the Pareto front of solution. Now, this Pareto front of solution is actually a front consisting of a large number of solutions, where each of the solutions are nothing but the optimized solutions, and Now, the user can select any one depending on his choice. Now, each of these particular optimal solution is nothing but the model of a particular car. Now, Mr. X is going to select any one out of these optimal solution. So, this is the way actually he can solve this type of two objective optimization problem. Now, this front is known as the Pareto front of optimal solution or Pareto optimal front of solution according to the name of its proposer. He is Wilfredo Pareto, and according to his name. So, this particular the front is known as Pareto optimal front of solution or Pareto front of optimal solution. Now, here the same thing I have put it, the Pareto optimal front of solution is nothing but the locus of all solutions, obtained after putting different weights on the objectives, and this has been named according to the name of the proposer, that is Wilfredo Pareto. Now, here, so I have considered only two objectives and our aim is to minimize both objective 1, that is f 1, and objective 2, that is f 2. Now, here actually what we do is we try to minimize both f 1 and f 2, supposing this is cost and accident rate. Now, if I select a particular point on this particular front, so this is my f 2 and this is f 1. Now, if I consider the higher value of this particular f 1, so I will be getting the smaller value for this particular f 2. Now, that means these two objectives are fighting with each other, they are conflicting, and if they are found to be conflicting and if there is a trade off between f 1 and f 2, so then only we will be getting so this type of Pareto optimal front of solution. Now, let me take another example. Now, here I am just going to show another variation for this particular f 1 and f 2. Now, corresponding to this particular point, so this is my f 2, this is f 1, corresponding to this particular point. So, this is my f 1 and this is f 2. So, as f 1 increases, so f 2 is going to decrease. So, they are conflicting. So, this is another valid Pareto optimal front of solution. So, this is a valid Pareto optimal front of solution, this is another valid Pareto optimal front of solution. Now, here I am just going to show another possibility. Supposing that, so this type of curve, now if I select a particular point lying on this particular curve, so I can find out f 1 and f 2. Similarly, another point if I consider, I can find out f 1 and f 2. So, here as f 1 increases, f 2 is going to be reduced and once again they are fighting with each other, and this is another valid Pareto optimal front of solution. Now, I am just going to take a few other examples and where we can see that they are not the valid Pareto optimal front of solution. For example, if I take so this particular the solution. So, this is f 1, this is f 2. So, our aim is to minimize both f 1 and f 2. Now, if I take a particular point here, so this is my f 1 and this is f 2. If I take a second point here, so this is my f 1 and this is f 2. Now, from point 1 to point 2 if I move, so both f 1 and f 2 are increasing. So, there is no fighting between f 1 and f 2. Now, by definition this is not a valid Pareto optimal front of solution. So, this is not a valid Pareto optimal front of solution. Now, similarly, if I take another example, so we can find out that this is another where this is f 1 and f 2 and our aim is to minimize both f 1 and f 2. And once again if I take say a particular point, say point 1 here, so this is my f 1 and f 2, another point, so this is my f 1 and f 2, and in this particular direction say 2 to 1 both F1 and F2 are decreasing. So, there is no fighting attitude between F1 and F2. This is once again not a valid Pareto optimal front of solution. This is also not a valid Pareto optimal front of solution. Now, here we have considered two objectives and our aim is to minimize both the objectives. Similarly, I can consider another problem where my objectives will be to maximize both the objectives F1 and F2, and if that is the case, now in that case, so there is a possibility I will be getting some Pareto optimal front of solution. Now, let me take a very simple example. So, here my aim is to minimize both F1 and F2. Now, let me consider another problem where I am just going to maximize both F1 and F2, two objectives F1 and F2. So, our aim is to maximize both F1 and F2, and supposing that I am getting a front like this. Now, let me check whether this is a valid Pareto optimal front or not. Now, let me consider a particular point here. Now, corresponding to this particular point, so this is my F1 and this is F2. Another point is here, say point 2. So, this is my F1 and this is my F2. Now, here you see, here F1 is less, F2 is more, and here F1 is larger compared to the previous F1, but F2 is smaller. So, here as F1 increases, F2 is decreasing. So, that fighting attitude is there. That means, this is also a valid Pareto optimal front of solution if I want to maximize both F1 and F2. Now, to summarize, actually I just want to say that if there are two objectives, I can consider either to maximize both the objectives or to minimize both the objectives in order to find out the valid Pareto optimal front of solution. Now, here I just want to put a note that any optimization problem having two objectives may not be a candidate problem for obtaining the valid Pareto optimal front of solution. Now, these are the examples. Now, this is also a two objective optimization problem F1 and F2, and supposing that I am just going to minimize both F1 and F2. Now, here there is no conflicting nature between these two objectives, they are not fighting with each other. So, this is not a valid problem for obtaining the Pareto optimal front of solution, although this is an optimization problem having two objectives. So, once again let me repeat, any problem having two objective function may not be a candidate problem for obtaining the Pareto optimal front of solution. So, this is actually what we mean by the two objective optimization problem and how to find out the Pareto optimal front of solution for the problems having two objective functions. Now, I am just going to extend this particular problem to a more complicated situation. Now, the situation is something like this. Supposing that in place of two objectives, I have got three objectives. Now, the objectives are as follows. Supposing that the first objective is minimize F1, second objective is minimize F2 and the third objective is minimize F3. Now, I can also state in place of minimization like in the form of maximization. For example, I can write down maximize F1, maximize F2, maximize F3. So, either we can state as a minimization problem or as a maximization problem, and supposing that the objectives are such that they are fighting with each other. Now, if this is the situation, so I can find out one Pareto optimal front if I consider like F1 versus F2. So, there is a possibility I will be getting some Pareto optimal front. Now, if I consider say F2 and F3, there is a possibility that I will be getting another Pareto optimal front, and if I consider like your F1 and F3, so there is a possibility I will be getting another Pareto optimal front. Now, what you will have to do is there are 3 objectives. Now, these 3 Pareto optimal front I will have to superimpose just to imagine what should be the Pareto optimal surface. Now, as there are 3 objectives, so I will have to visualize the Pareto optimal surface. Now, what I can do is I can superimpose these 3 Pareto optimal front and I can visualize the Pareto optimal front of surface, because this will be in 3 dimension. Now, we human being we can visualize only up to 3 dimension. So, this particular the Pareto front of surface we can visualize. Now, this is called actually the 3 objective optimization problem. Now, let me take a very simple example, very practical example. Now, we the faculty members we have 3 very distinct responsibilities. For example, we should be a good teacher, we should be a good researcher, we should be a good administrator. So, we have got 3 objectives and all 3 will have to maximize. So, this is nothing but a 3 objective optimization problem, and there are some functional constraints. For example, say a particular day consists of say 24 hours and a person cannot work efficiently more than say 13 hours or 14 hours in a day. At the same time, actually there will be a few constraints set by the surroundings. These are all the functional constraints. And what are the variables? What are the variable bounds? For example, a person will have some capability to work hard, he will have some level of intelligence and he will have some level of physical strength and mental strength. These are all design variables. So, I have got 3 objectives: maximize the teaching performance, maximize the research performance, maximize the performance of administrative work, and I have got the variable bounds, and there will be some functional constraint. This is a very good example of a constraint optimization problem. Now, the responsibility of the faculty member is to visualize that Pareto optimal surface, so that he can perform in the optimal sense. So, this is the example of the 3 objective optimization problem. Now, I am making it more complex. Now, if I just add another objective, like the same faculty member should also do little bit of social work. Now, he will have to maximize the 4 objectives. The moment he consider 4 objectives, so there will be some Pareto optimal surface, but it will be very difficult or it is quite impossible to visualize, because it is in 4 dimension. So, if this particular multi-objective optimization problem is having like 4 or more than 4 objectives, those problems are bit difficult to tackle, and these are actually popularly known as many objective optimization problems. Now, to solve this many objective optimization problem, we will have to use a slightly different type of approaches, and that particular study on many objective optimization is beyond the scope of this particular course. So, here what I am just going to do is, I am just going to handle the 2 objectives and 3 objectives optimization problem, and I am just going to show how to tackle so this type of multi-objective optimization problem. Now, if you see the literature, we have got a large number of tools or the methods available to solve this type of multi-objective optimization problem. Now, if you see the oldest approach, now this oldest approach is actually the weighted sum approach, and this is a very simple approach. The principle I have already discussed little bit, but I am just going to discuss in much more details. There are some traditional other approaches, and after that the principle of the non-traditional optimization tools have been used to tackle this type of multi-objective optimization problem. So, gradually actually I am just going to discuss these methods, these tools one after another. Now, let me start with the first approach, that is called the weighted sum approach. This weighted sum approach actually, as I told, that we try to formulate this multi-objective optimization problem as a single objective optimization problem. Now, let us consider that an optimization problem has got capital N objectives. So, there are capital N number of objectives. So, I can formulate like this: minimize f I capital X. Here I varies from 1 to up to n. There are capital N number of objectives, and this capital X is nothing but the collection of small m number of small x values. So, this is in it is having m numerical values. Now, our aim is to minimize this particular multi-objective optimization problem. Now, let us see how to tackle this. Now, to tackle this, actually what we do is, so this multi-objective optimization problem is transferred into a scalar or a single objective optimization problem as shown below. Now, the same problem that is rewritten in the form of minimize summation I equals to 1 to n. So, capital N is nothing but the total number of objectives W I multiplied by f I x, where this W I are nothing but the weights lying between 0 and 1, and the sum of these W values, that is summation W I varies from 1 to n is equals to 1.0, and of course, the design variables will have some range. Now, that means here if I just want to put it, this particular design variables, that is x, should be greater than equals to x minimum, and it should be less than equals to x maximum. So, this is nothing but a constrained optimization problem. For example, say, so this is nothing but the objective function. Now, this is the functional constraint and this is the variable bound. So, this is nothing but a constrained optimization problem. Now, to solve this particular problem, if you see some literature, many people have used the traditional method of Lagrange multiplier. Now, I am not going for that. So, using the Lagrange multiplier, so this particular optimization problem can be solved. Now, this is one way of solving. Now, what I am going to do is, I am not going to follow this Lagrange multiplier here. So, instead what we do is, I can convert it into a single objective, and by setting a proper values for this W 1 and W 2, if it is a 2 objective problem. So, I can find out the Pareto optimal front of solution. Now, this particular multi-objective optimization problem, let me consider this is a 2 objective optimization problem, and our aim is to minimize say both f 1 and f 2. Now, for simplicity, so I am considering that capital N is equal to 2 here. Now, what we do, as I told, that we try to find out a single objective thing, that is nothing but your. So, I will have to minimize in single objective form, that is nothing but f 1 multiplied by W 1 plus f 2 multiplied by W 2. Now, what we do is we select one set of W values, that is nothing but W 1 1, W 2 1, and solve this as a single objective optimization problem. And if you solve this as a single objective optimization problem, so I will be getting a particular optimal solution. Now, if I change this particular W values to another, and of course, the sum of W values should be equal to 0. So, if I take another set of W values, there is a possibility I will be getting this as the optimal solution, another set of W values this as the optimal solution, and as I discussed already, I will try to find out the locus of this particular optimal solution, and this is nothing but the Pareto optimal front top solution. So, this is actually the oldest of all the approaches to handle so this type of multi objective optimization problem. Thank you.